We will calculate the process capability from a set of linear measures, which we assume are normally distributed. We are looking for the process capability index, CPK, the maximum possible process capability, CP, and the parts outside of the tolerance limits in 1 million manufactured parts, PPM. Furthermore, we will plot the results with this chart. The frequency distribution is shown in blue. It subdivides the values into bins and provides information on how frequently values are contained in the respective bins. With this, we calculate the probability mass function. It is shown in orange and allows us to evaluate the process graphically. The tolerance limits are shown in red, and the 6 sigma limits of the probability mass function are shown in green. Let's jump to Excel. First, we call our sheet process capability. Then we have to import the data. In our case, the data is from an external file, so we have to import it. We click on Data, Import from Text, select the data, click on Import. And because the delimiter in our case is a tab, we have to select this, click on Load, and here we go. It is formatted as a table, we don't need this, so we click Convert to Range. And now we can easily copy and paste it where we want to have it. Next we need bins, but we don't know from which to which point the bins should reach, so we have to calculate some stuff. First things first, the upper tolerance limit, UTL. In our case, this is a number from the drawing and it's 1.25. And the same is true for the lower tolerance limit, LTL. It's 1.15. We can format it so it looks a bit prettier, make it yellow, give it a border, and now we start to calculate things. We click on Insert Symbols and we choose the microsign because it is the commonly used sign for the arithmetic mean. We use the Excel formula average and put all the data in. Press enter and we calculated the arithmetic mean. And next we insert the symbol sigma because it is the commonly used letter for the standard deviation of a sample. Excel works with the formula stdiv, and we also need all the data for this formula. So we calculated this. And next we can calculate the upper 6 sigma limit. Like the name says, it's the arithmetic mean plus 6 times standard deviation. And then next we calculate the lower 6 sigma limit. And this is the arithmetic mean minus 6 times standard deviation. Alright, now we have enough information for our bins. The bins have to include everything, both tolerance limits and both 6 sigma limits. So the bins should start at, let's say, 1.00 and reach at least 1.36, so let's make 1.40. Select it, grab the box and pull it down till we reach 140. All right. Now we can calculate the frequency. Because it is an array formula, we have to select all fields in advance. And now we can use the formula equals frequency. The array data is our data. The bins array are our bins. Now we have to pull Control, Shift and Enter to calculate the array, and here we go. We create a new sheet and call it chart. We click on Insert, 2D column, make it a bit bigger, and insert the data by clicking on Design, select Data and Add. The series name is the frequency field, and the series values are all the data we calculated for the frequency. The category axis are our bins, and by clicking on OK we can see the frequency. Alright, let's head forward and calculate the probability mass function. It is also an array function, so we also have to select every field in advance. And then we can use the formula equals norm.dist. The x means the bins we created. The mean means arithmetic mean. The standard deviation means standard deviation. And cumulative means false, because we want to have the probability mass function. We have to use Control, Shift and Enter to calculate, and now we can look in the chart what we've done. But first we have to import the data. So we click on Design, select Data and Add. The series name is the probability mass function field. The values are the values, and the category axis are our bins. Now we see what we calculated in orange, but this doesn't look really good. So we said change chart type, click on combo and change the chart type of the probability mass function to line. We say it's the secondary axis and click OK. To give it a smoother look, we can say fill line and smooth line. And because the secondary axis is above the primary axis, we can fix that by saying, well, double clicking to the secondary axis and change its minimum to 0. Now it looks pretty good. We can proceed with our calculations and calculate the cumulative distribution function. We need this to calculate the probabilities later on. It is also an array formula, so select every field you need in advance and write the formula equals norm.dist. The x are the bins. The mean is the arithmetic mean. Standard dev is standard deviation, and cumulative is true. Use Control, Shift and Enter, and we've got our calculation. We can look what we've done by adding a new chart, and we choose a 2D column chart. We click on Design, select Data, and add the newly created data. The values And as always, the bins for the x-axis. For better luck, we can change the chart type to line and smooth the line. And that's it, our cumulative distribution function we have to calculate with. All right. And next we want to calculate the Six Sigma limits. We already calculated them, but we want to show a bar in the chart where they are. So we have to calculate some things to do this. The first thing is we need the maximum of the vertical axis, and we do this with our primary axis. We use the formula max. And we use the frequency values. So we get the maximum frequency, and that's 17. And now we calculate these Six Sigma limits. Thing we want to do is, if the bin corresponds to the upper or the lower Six Sigma limit, then we want to write a 17. If it is not the case, we want to write a 0. So we do this with the formula equals if the bin equals to the upper Six Sigma limits, and we round this to 2 digits, then we want to write the maximum. And if this is not true, we want to do the same thing for the lower Six Sigma limit. So we write if the bin equals to the lower Six Sigma limit, and we round it to 2 digits, then write the maximum vertical axis. Otherwise, write a 0. And we can grab this function and pull it to the end. And now we see we've got a 17 at 1.36 and we got a 17 at 1.02, and that's exactly the sigma limits rounded to 2 digits. Have a look what we've done in the chart. So we select the chart, click on design, select data and click on add. The series name is the Six Sigma limits field. The series values are the values below. And the category are our bins. Well, we've got something, but it's a line, and this doesn't look pretty. So we click on the chart and say change chart type, and the series name Six Sigma limits we change to column, and say it corresponds to the primary axis. Yeah, that's exactly what we wanted. Let's do the same thing for the tolerance limits. Let's write tolerance limits. And now add the formula. If the bins equals to the upper tolerance limit, then write the maximum vertical axis. Otherwise, if the bin corresponds to the lower tolerance level, then write also the maximum vertical axis. And otherwise, write a 0. We grab the box, pull it down, and now we've got a 17 at 1.25, and we got the other 17 at 1.15, and these are our tolerance limits. We can add this to our chart by clicking on design, select data, add the series name is tolerance limits, and the series value are the values we created. And the category axis are the bins. Like before, we have to change the chart type to a column and link it to the primary axis. All right, that looks great. Now we have to change the chart style a bit so it looks better. Well, this looks good, and we want to have a color change for the tolerance limits. So we select the tolerance limits and say no border and make it red. And same thing goes for the Six Sigma limits. We say no border and make it green. All right, this looks good. We can now click on the chart and say, well, add something, an axis title. And we want to have from the primary axis an horizontal title and vertical title, and from the secondary axis a vertical title. Well, they are caps at the moment, so we have to click them, make a right click and say font. We can change the all caps to normal, and now we can say, well, this is the frequency. And the frequency is measured in pieces. Let's do the same thing down here and say these are the values and they are measured in millimeters. And the last one is the probability mass function. And this is a function of the arithmetic mean and the standard deviation. The title's still missing, so we add it. Chart title, and we call the chart process capability. That's it, we are finished with the chart, but we have to calculate our process capability index, CPK. For this, we need the minimum of the both calculations, upper tolerance limits minus arithmetic mean, or arithmetic mean minus lower tolerance limits. And we have to divide the minimum by 3 times standard deviation. And that's the CPK. It's a number, 2 decimal places are enough, and it's at 0.5. The second thing we want to know is the CP. And that's the maximum possible process capability we can reach if the arithmetic mean is right in the middle between the upper tolerance limit and the lower tolerance limit. Its calculation is upper tolerance limit minus lower tolerance limit divided by 6 times standard deviation. So that's the maximum, 0.59. And we also can format it as a number with 2 decimal places. Next thing we want to know, the parts within the tolerance limits if we manufacture 1 million parts. For this calculation, we need the cumulative distribution function. And what we do is, we say, well, we need the value where the bin is the same as the upper tolerance limit. And from this value, we have to subtract the value of the cumulative distribution function, where the bin is the same as the lower tolerance limit, and multiply our calculation with 1 million. So let's do this. We need the VLOOKUP function of Excel for this. And say look up the upper tolerance limit in the array from bins to cumulative distribution function. Our call index we are looking for is 1, 2, 3, 4, 5. And we're looking for the exact match. And if we calculated this, we have to subtract the same thing where we look for the lower tolerance limit. We look for the lower tolerance limit in the same array table. We are looking for the 5th column and for the exact match. And everything, the whole calculation, we have to multiply with 1 million. Alright, we get a comma separated value, and this means there are 0.38 parts. In reality, there are no 0.38 parts, so we have to say it's a number with no decimal places. We can use the thousand separator, and we got 912,773 parts within the tolerance limits if we manufacture 1 million parts. The next thing is easy to calculate. It's called PPM. And these are the parts outside the tolerance limits if we manufacture 1 million parts. And it's easy. It's 1 million minus the bad parts. 87,227. That's it. That's everything we wanted to know. We can make it look a bit prettier by saying, well, it's blue and at the border. But that's really it. So thanks for watching.